case. Cool. I'm Dominic. Bruno asked me to take two of these lectures as part of this course on Black Hole Thermodynamics, lecture 3, which is today on the first law of black hole mechanics, and lecture 6 on physical aspects of black hole evaporation, which is a somewhat arbitrary title for an eclectic array of topics which I'll talk about in varying levels of detail. I'm a philosopher of physics at the London School of Economics. Given I'm a philosopher of physics, I'm hoping to be able to meet physicists and mathematicians halfway in this lecture and get all of the rigor and detail that you might need. But I might see some things somewhat differently or move through things at a different speed to what you would prefer. Feel free to ask me questions, and anything that I can't handle, I'm sure Bruno will be on hand to help us out, and we'll all work together to have a good picture of the first law. Okay, this is lecture 3. First law of black hole mechanics. I'm aware I've also not always got the most legible handwriting, so if anything, if I say something too fast and you can't see what I've written, feel free to stop me and ask me what I've written. I won't be offended. The same with my accent. If you don't understand anything I say, just ask me again. Okay. The goal of this lecture is to derive the first law of black hole mechanics. This is a super important law in black hole thermodynamics because it really closely resembles the first law of black hole of thermodynamics. That's written du equals dq plus dw. So this is what we're aiming for, where u is the internal energy, q is the heat flow, and w is the work done. Now this is normally written like this, where T is the temperature, S is the entropy, P is pressure, and V is volume, plus any other work terms we may have. And that looks just like what our first law of black hole mechanics is going to look like. So to jump to the end, first law is going to look like dm equals 1/8 pi kappa dA plus omega h djh, where kappa is the surface gravity. We met that in the last lecture. A is the area of the event horizon. Omega h is the angular velocity of the black hole at the event horizon, and jh is the angular momentum. Note that there's normally another term here for a charge term, but I am ignoring that for this lecture because everything looks extremely similar. You can do everything with charge, and it just means I have to write fewer terms and talk less. So we're just dealing with Kerr black holes today, which are parameterized by mass and angular momentum and nothing else. But we can easily extend all these results. So just to give an overview of what's going on here, the zeroth law of black hole mechanics doesn't really inspire an analogy with thermodynamics on its own in any way, but the first law really does, because it's not just formally analogous, but it's also starting to get physically analogous. So this mass term, dm, is just the internal energy of black hole. Mass is energy in gravitational physics, of course. And so we've also got something of a physical analogy, and this is also really a work term. As I'll discuss more in lecture 6, the rotational energy of a black hole is very closely related to how much work you can do with that black hole, even before you've spoken about quantum aspects. The obvious disanalogy is this term, because classically, the temperature of a black hole is going to be 0 because supposedly it can't emit radiation. So normally it's stated that black hole mechanics are just formally analogous to laws of laws of thermodynamics until the derivation of Hawking radiation. I'm actually not sure I believe that statement, but that's the consensus. In lecture 6, I'll talk a bit about Hawking radiation, but not much because it was covered in the quantum field theory and curved space-time course. But we will talk about black hole thermodynamics. So our job today is to derive this. This is going to be done in 4 parts. In order to have these quantities like mass, area, angular momentum.
Sorry, can I interrupt for a question?
Yeah.
So the temperature is not as worse. Analogically, the temperature is not as bad as the entropy, right? So if we try to define the black hole entropy, that quantity is formally divergent. Like it has an edge bar sitting in the denominator, and then when you take the strict classical limit, it's formally divergent. So how do you even make sense of an entropy classically for the black hole?
It depends how you want to do it. I mean, you can be super formal and demand it's based upon micro degrees of freedom or something like that. But if you follow Bekenstein, you just look at the second law, which we covered in the next lecture, and you write something like S proportional to some constant times A.
Right.
A here, and you just say that's what the entropy is, and you just deal with it. You don't try to do anything complicated.
But then the constant A will contain the Planck constant in the denominator, right? If you do some sort of dimensional analysis, or if you just compare with the temperature, if you identify temperature with kappa up to some factors, you see that there is an edge bar sitting in the denominator for entropy. And when you take the classical limit, that entropy is divergent. So what do we say when we say entropy classically? What do we mean? Like, do we mean something, or it's just a formal
statement? I mean, I don't want to get too hung up on this because we don't need to treat it classically. But there's no need for us to take the classical limit. You can just say we don't have a theory of quantum gravity or something like that.
No, why it bothered me was because the Carter-Hawking paper is a classical paper, right? It's not really a semi-classical analysis. It's purely.
Yeah, but we believe that the universe is quantum gravity. And so just because we're dealing with the semi-classical approximation, I can still have Planck's constant, and like things go wrong as things might go wrong as I take the classical limit, but that's just going to tell me that like deep down there's something going on quantum maybe.
I see. So at the Carter-Hawking level, it's just a formal analogy, right? Only when you include the Hawking analysis, you see that there is something truly.
That's consensus in the community.
I see.
Yeah.
Thanks.
So we're gonna do this in 4 parts. First, we're going to learn how to do integration on differential manifolds, because we're going to have to integrate over some sort of surface in order to get M, A, and JH. And so we're going to learn how to do that. Then we're going to define those quantities, which are going to be called Kolmar integrals. So aspect 1 is going to be integration. 2 is going to be Kolmar integrals. And 3, we're going to derive a form of the first law, which I refer to as the integral form, which doesn't look like this and refers to absolute quantities like M rather than dm. And then we'll finally derive the differential form. And we'll do that 2 ways if we have time. Let's see. Okay. Let's get into it. Section. Let M be a differential manifold. Then a P form on M is an antisymmetric 0p tensor on M. Then we define the exterior derivative of a P form. Let's say alpha is our P form, as the exterior derivative is going to be d alpha, and indices are going to range from A1 to AP plus 1. It's going to be P plus 1 nabla, and then anti-symmetrize over all the indices. That's our exterior derivative. And it quite clearly is just what normal differentiation looks like. A manifold of dimension n is orientable if it admits an orientation. An orientation is a smooth, nowhere vanishing n form. We're going to epsilon A1 to AN. Okay? So because it's a smooth, nowhere vanishing n form, E prime is equivalent to E prime, which is defined as FE, is equivalent given that F is everywhere positive. So two orientations are equivalent if F is everywhere positive and it obeys that equation. An orientation is right-handed in a chart, in a coordinate chart, if it's everywhere positive in that chart. And left-handed if it's negative. Good. A result which will be important later is that any n form X.
Sorry, in the definition of the exterior derivative, do we need the covariant derivative on the right hand side? The nabla symbol that you wrote down.
Yes.
Okay. And what is the last word in the definition of the form?
In the definition of what, sorry?
In the definition of a P form, the last word that you wrote down.
Let me scroll back up. On M.
Okay, thanks.
No worries. So any M form is related to an orientation. By some function h, so by x equals h, where h is a function. Good. So x will also define an orientation if h doesn't vanish, obviously. And so an orientable manifold admits precisely two inequivalent orientations. There would be a left-handed one and a right-handed one, positive and negative. Good. Now we're going to find a volume form. So on an oriented manifold with a metric, the volume form is defined by epsilon 1 to n equals square root of g. Where these are actually, these are no longer abstract indices, these are sort of real valued indices. Well, not real valued, they're coordinates. Important result, and so I'm going to call it 1 because I'll refer to it later, is that the contraction of two volume forms on an n-dimensional Lorentzian spacetime is given by the following. Epsilon 1 epsilon A1 to AJ plus 1 to AN. So we're contracting over the first J indices. That should be B1, N, but 1 minus N minus J factorial, J factorial, and then just continuing this down here. Delta AJ plus 1, BJ plus 1, 2, AN, BN, and desymmetrized over the top indices. Good. So now let's do some integration. M is an orientated manifold. Manifold of dimension n. And let psi be a map from some region of M into U, which is a right-handed coordinate chart given by the coordinates xu, mu, sorry, and let x be an n form. Then the integral of x over the region O is defined by dx1, dxn, x. N. That's how we define our integration of an n form over some region. It's not hard to show that this is chart independent. I'm not going to do it here. We can also extend this to over all of M by summing over the integration of all charts in an atlas weighted by some partition of unity, and that integration of all of them will also be independent of the partition of unity we choose. I don't do that here because it's extra writing for really no gain. You can extend this to over all M in a fairly trivial way. So then the volume of M is defined as the integral over a volume form. And the integral of a function f on M is just given by the integral of that function with the volume form. So, I mean, there's an ambiguity. I originally was using epsilon to be at any orientation. From now on, I'll always use it to be the volume form. Okay. So now the result we're going to use a bunch of times in this lecture is going to be Stokes' theorem on manifolds. Oh dear. Let me do that again. Is that back for everyone now?
Yes.
I should say. Good. So quickly, I won't write this down because this won't be used again, but a manifold of the boundary is defined in the exact same way as a manifold, except that the charts that the manifold is going to map to are open subsets of the half Rn space. So it's Rn, but one of your coordinates is bounded positive semi-definite. So let's say one of your coordinates is t, you would say that t is greater than or equal to 0, and then that becomes a boundary. It's super intuitive, super natural, that's how you do it formally. So then we get Stokes theorem in general relativity. Let M be an n-dimensional compact oriented manifold with boundary. And let alpha be an n-1 form on M, then the integral over M for the exterior derivative, alpha, is equal to the integral over the boundary of M, where I use a dot to represent the boundary of alpha. And D is exterior derivative. So this is how Stokes' theorem looks on differential manifolds. And with that quite definitional preliminary out of the way, we can get to a bit more physics, Como integrals. So all we want is to be able to write down an expression for the mass energy of a black hole space-time, or any space-time for that matter. In general relativity, the stress energy tensor is given by TAB, which represents the energy properties of matter. Using this, the local energy properties relative to any observer will be well defined. And also we can write down our local energy conservation law, TAB equals 0, which is defined at every point. Now, in special relativity, this local conservation law implies a global conservation law with respect to an inertial time coordinate in a very simple way. Whereas in general relativity, this isn't going to lead to a global conservation law. The exception is going to be if we have a time-like killing vector field, which Bruno defined in the last lecture. And then we do have a global conservation law. I'm going to write that down now. Just as a heads up, the conservation law I'm going to be writing down isn't going to be what we're going to use. It's not going to be interesting, but it's going to be a first chance to see a few techniques and applications of Stokes' theorem, which are going to be used for next hour and a half. So, lemma 3.1. If a space-time admits time-like killing vector field xi, then for any, but it's 3.1 because that's what it is in my notes. Sorry. For any two space-like hypersurfaces, sigma and sigma prime, which bound a region R, the total energy of matter on sigma is equal to that sigma prime, where the total energy of matter is given by minus the integral over some Cauchy surface A1, epsilon A1, A2, A3, B, T, B, C, Xi, C. Okay, so basically the lemma states E is a conserved quantity. So let's prove this.
sorry, but does Zaya require to be time like everywhere, or should be time like at infinity only? This scaling field.
Pardon?
Yeah.
Sorry, I didn't hear that.
Yeah, I'm asking, does psi require to be time like everywhere, or we need it to be time like at infinity only? I mean, this scaling field.
Am I requiring the kinetic field to be time-like everywhere, or time-like just at infinity? Is that the question?
Yeah.
I think I'm requiring it to be time-like everywhere. But I'm not sure that's used anywhere in the proof, so maybe we can think about that.
Okay.
I'm going to be integrating this over, but yeah, I'm going to want it to be time-like everywhere, I think.
Okay.
So first, this is going to be true. Nabla A are integrated over TAB XIB. Just product rule. This is 0 by our conservation law. And this is 0 by Kinning's equation, because TAB is symmetric, and by Kinning's equation, nabla A psi B is antisymmetric, so that's equal to 0. Now let sigma and sigma prime bound R. So we've got something like this. And then by Stokes' theorem, E on sigma prime minus E on sigma equal to just integrating over the boundary of R. So that's R dot there. So we're just integrating over the boundary. And that step's trivial. And then by Stokes' theorem, we get this where I'm explicitly writing the exterior derivative. It's now of R. Okay, and then we can move nabla through our volume form. And so we get epsilon A1, A2, A3, B. Just in case this notation isn't familiar to everyone, when I draw a line like this inside anti-symmetrizing over indices, it means I don't anti-symmetrize over the things so the line stops anti-symmetrizing and it recommences when the line's after the next line. So here I'm anti-symmetrizing over A1, A2, A3, and D, and ignoring and not anti-symmetrizing over B.
Sorry, but here sigma and sigma prime are hypersurfaces, so they are non-compact. They bound a non-compact region, right? I mean, they extend all the way up to infinity.
I mean, they're hypersurfaces. I mean, if they extended out to infinity, you could just do it like that. They don't have to extend out to infinity. They just have to be hypersurfaces which bound a region.
So sigma and sigma prime doesn't need to be Cauchy surface. It's just any hypersurface space like.
Pardon?
I'm asking sigma and sigma prime doesn't need to be Cauchy surface. It can be any space like hypersurface.
Yeah.
Okay.
So then we know that so this is an n form now, where n is 4. And so we know that must be proportional to our volume form. So we can write A1, A2, A3, B, D. TBC XIC equals H, where H is some function. Okay. Now we contract the left-hand side and the right-hand side with our volume form. And then by equation 1, which I wrote down, which is the contraction of volume forms, remember? This gives us nabla B, T, B, C, nabla C equals H. And we know that this is 0, so this must be 0. And so H is 0, H is equal to this, so the integrand must be 0. And so we've learned that E sigma prime minus E sigma equals 0, which is what we wanted to prove. It's the energy is independent of our Cauchy surfaces. I mean, I went through that basically to show you the use of some of the integration tools I just defined. But E is of no use for us for defining the mass of a space-time. We've at no point used the Einstein equation. And so TAB can't be describing the total energy of the space-time, which in any useful sense captures the energy possessed by the gravitational field. For example, if I have a black hole in the vacuum space-time, this notion of energy isn't going to capture that at all. Indeed, TAB need not be the tensor that appears on the right-hand side of the Einstein equation. So we're clearly missing something. Unfortunately, we can't write down a TAB for gravitational energy because there's no meaningful notion of energy density of the gravitational field in general relativity. Not one which satisfies all the things we'd want, all the conditions we'd want it to. And so we can't state a local conservation law for gravitational energy, which is just used in the proof. But we can write down a useful notion of total energy of an isolated system, where we model isolated as meaning asymptotically flat. And this is how we're going to do it. The main derivative water we're going to want on any adequate account of the mass of a space-time, which contains a mass m, where we're not thinking of mass m as like the mass of matter now, is that for a particle at r much larger than m, where I'm using geometric coordinates. This should behave as if it's acted on by the Newtonian mass of mass m. It should behave as if acted on by the Newtonian mass m. So basically the picture is you've got a black hole, you've got a particle infinity, but the black hole is a vacuum solution. If the particle behaves as if in the middle of the space-time there is a Newtonian mass m, we're going to ascribe a mass m to that black hole space-time. To figure out what expression is going to capture this, we're going to model a shell of unit mass density, not fine, in a stationary region, of unit mass stationary. Sorry, I'm going to model the force required to keep this shell stationary, defined as following Killing vector fields, around a region of space-time in here, which contains all the relevant gravitational energy because asymptotically flat. So at infinity, we're going to think there's no gravitational energy. And we're going to find that this expression has the same form as the Newtonian expression for a shell around a mass m. Then we're going to equate the expressions, and that's going to be our expression for the mass of a space-time. To do this, we're going to need another lemma, which seems just very technical, but it's going to be required. It'll be nabla A acting on epsilon BC DE and anti-symmetrizing over ABC. Nabla DXI E is going to be equal to 2/3 R ED psi D epsilon E A B C. I mean, we're already feeling better because we've written down the Ricci tensor. So the Einstein equation is going to be getting involved somewhere, which is a good sign. Let's quickly prove this. Epsilon A, B, C, D, nabla B, epsilon C, D, E, F, nabla E, X, I, F. We can move nabla through, and so we get epsilon A, B, C, D, epsilon C, D, E, F, Xi B, Xi E, E, F. And then using 1, this is just -4 nabla B, nabla anti-symmetrized over A, Xi B. And then using Killing's equation, sorry, 4 is equal to nabla B, Xi A. Okay. Now, using the Killing property and the Ricci identity, one can prove, I think Bruno wrote this down in the last lecture, I don't remember. This is true. I don't do it here. It's a reasonable bit of homework to do this. And this implies just contracting over the A and B indices. So it's B. Thus, using this with what we just proved, we can write down epsilon A, B, C, D, nabla B, epsilon C, D, E, F, nabla E, Xi, F is equal to -4 R, A, B, R, A, B, B. And then just contracting with the volume form again gives you the result. I'll write down the result again because we're about to use it. My Xi's get worse and worse. Let's call this 2 because I'll switch on in a sec. Okay, so now we're going to model our stationary shell of mass around surrounding a region full of gravitational energy. Consider a static, asymptotically flat space-time, which is vacuum. Space-time is vacuum near infinity. Okay, so we're going to normalize our Killing vector field A. So the norm Xi, so the norm is defined as Xi contracted tends to 1 at infinity. Okay, so in the forward velocity of a particle on an orbit of Xi, i.e. it's a stationary particle, is VA equals, I'm aware I'm getting dangerously close to repeating what Bruno did on Wednesday, but I'll continue nonetheless. And so the for acceleration is just AB equals VA nabla A VB. And then, as Bruno did discuss on Wednesday, the force that must be exerted, this is just the force, the local force that must be exerted to hold a unit rest mass in place. And the force that must be exerted at infinity is redshifted by a factor of the norm of xi to give a tilde B VB nabla B A VA nabla A xi B. Bruno discussed that on Wednesday. Thus, suppose we have our shell S of unit surface mass density in the Cauchy surface. This is our Cauchy surface now. Orthogonal to VA. Right. Then the force required to keep this entire unit mass density shells on a stationary orbit is just the integral of tilde AB normal to the surface S over the surface S. So that's going to be F equals the integral of S NB VA nabla A xi B epsilon CD, where NA is the unit normal to S, and epsilon CD is the volume element on S. Good. By Kinning's equation, and nabla A xi B again is antisymmetric, and so we can throw away the symmetric part of NB VA because that's going to be 0. And we just have the antisymmetric part VA NB antisymmetrized over the indices. And let's define capital N AB as a 2-0 tensor as 2 times that quantity, and that's going to be the unit tensor normal to S. So it's basically the tensor you get by tensor producting the 2 vectors which are normal to S. Thus, -6 and -6 just comes from like the antisymmetric factors or cancelling out and stuff. NAB epsilon CD is just the natural volume form on the entire space-time. Substituting this in to our expression for F, we get F is -1/2 integral over S A B C D C. Maybe it's a good exercise to make sure to track where these factors are coming from. But they're just come from adding various forms of the antisymmetries together. Now we want to show that this expression for the force is independent of the surface S. Obviously, we don't want our mass to be dependent on what specific integral we take at infinity. What specific Cauchy surface we take, sorry. Yeah. What specific shape shall we use? Especially because the Newtonian mass case is independent of that. So if we're like using this analogy with the Newtonian mass, it needs to be independent. So let S be entirely in the vacuum region of our space-time, then RAB is equal to 0 by Einstein's equation. We've used Einstein's equation. We're doing proper general relativity. And by the lemma 3.1 we proved, number A DE number D sine E equals 0. We can apply Stokes' theorem to any volume bounded by two surfaces S. So let's take two surfaces S, S prime. V is the volume bounded by them. And the integral over V some BC DE E. Applying Stokes' theorem, get two integrals over S and S prime. We've removed the exterior derivative. And this is equal to 0 because this is equal to 0 because it is equal to some proportional to the Ricci tensor, which is 0 because we're in the vacuum region. Good. And so our force is independent of S, which is what we wanted. Now, in Newtonian gravity, the force required to hold a shell of unit mass density in place is also independent of the shell, as I said, and it's equal to, this force is equal to 4 pi over m in the Newtonian case. Therefore, we equate these two forces.
Sorry,
And yeah.
what do you mean by vacuum here? When you say the space-time is vacuum near infinity, what is the vacuum meaning here?
TAB equals 0 near infinity.
Okay.
Just there's no matter.
Okay, so the stress energy tensor is localized within a finite region of the space-time.
Yeah.
Okay, thanks.
So then, equating the two forces, we get m equals -1 over 8 pi integral. Let me move this because I want to put a big box on this. Over some surface boundary in the region S, which has to be taken at the asymptotic limit in a vacuum. Epsilon A, B, C, D, nabla C, Xi, D. This is our core moments. This is the mass of all stationary asymptotically flat spacetimes that are vacuum near infinity. It's conserved and it's nicely associated with the Killing vector field, which is nice because this is the notion of energy of the spacetime. And of course, energy is defined by time translation symmetries, which in general relativity are given by our time-like Killing vector fields. It's also very similar to the Newtonian case in the sense that, as Bruno talked about later, the time translation symmetry is very closely related to whether you're feeling a force of gravity, whether you're following the integral curves of a Killing vector field. And this is basically the same equation as in the Newtonian case, where instead of our time-like Killing vector field, we have the Newtonian potential, which also tells you how you're feeling the gravity. And so even though they look like very different quantities, they represent very similar things. We've also used Einstein's equation in this derivation, making sure it's fundamentally general relativistic. Okay.
Hi, I have a question.
Yeah.
So this expression of Kolmar mass, is a non-local quantity, right?
Mm-hmm.
Oh, okay. And is there a notion of local or quasi-local mass?
No, not of the gravitational energy. people do write things down and do stuff with them, especially in philosophy literature, where we're really trying to think about these things fundamentally. But there's no really good one. There's no natural one. And you got to sort of bluff it a bit. You don't get proper tensors out. You get pseudo tensors.
Okay, and so you say that it corresponds to the Newtonian mass when we take the non-relativistic limit. Is that right?
Mm-hmm.
Yeah.
It's not like we're not taking a non-relativistic limit here. We're just sort of looking at how we're defining this mass by how a particle would behave in a Newtonian case, and saying, well, that's what we're calling the gravitational mass.
Okay.
So it's not like we're not taking any limit here. We're not taking a
see.
small perturbation. We're defining it as inducing particular behavior in the same way that Newtonian mass does.
Okay, got it. Thank you.
No worries. I state without proof.
When you say like it's independent of the choice of the S, does it mean like the S can be only chosen in the exterior in the vacuum region?
Yeah.
Okay, thanks.
But when we're doing asymptotically flat spacetimes here, and we're imagining an isolated system, so we're always going to be able to model infinity as a vacuum. I state without proof that you can prove that that the angular momentum of an axisymmetric spacetime is given by this very similar quantity, epsilon ABCD, nabla C, psi D, where psi A is the space-like filling vector field, which generates. Pardon? I'm sorry. Sorry, someone's looking at my office. One moment. Yeah. I put this till 6. I'm doing the lecture, sorry. I'm really sorry about that. Okay, yeah. Psi is the space-like filling vector field which generates the one parameter group of isometries isomorphic to U1, right? So it's just spherical, not spherical symmetry around an axis. J is the angular momentum of a space-time, and nicely, J and M, these Como integrals, this is the Como angular momentum, are equal to their equivalents in the Kerr metric. And so they're doing exactly what we want them to do. So these are nice. Now, the Como mass is only...
When you wrote the first law, you had that omega h and djh. Where does the h there represent the horizon?
Sorry, could you ask that again?
So when you wrote down the first law, black hole mechanics, in the expression you had omega h and djh. The h there represents the horizon, or is it something?
Yeah.
So this expression that you wrote down for J, is it the angular momentum corresponding to the horizon?
It's the angular momentum of the space-time. Properly.
Is it same or is it different
in black hole spacetimes, in Kerr, we then ascribe it to the black hole.
Okay. And so psi is one parameter. Sorry, I could not understand that. So it generates
Psi
what?
A is the killing vector field, which generates, so it's everywhere tangent to a one parameter group of isometries isomorphic to U1.
Okay.
Great. Now, the Como mass is only for stationary spacetimes. For non-stationary spacetimes, we use the ADM mass, And the ADM mass corresponds to the Como mass for stationary spacetimes. They give the same result. To do the ADM mass, we would have had to do a lot more work. You have to restrict to spacetimes which have a 3+1 decomposition, where the 1 is time and the 3 is space. And that allows us to write down a Hamiltonian formulation of general relativity. One finds that the Hamiltonian takes a particular form where there's a surface term, which is then identified as equal to the EDM mass energy. It's a whole bunch of small stuff to do. It won't appear in the proof I'm going to use, and so I haven't taught you it, but the generalized notion of mass for spacetime is the ADM mass. In many ways, Como is still the more useful. Isolated stationary spacetimes, but yeah, for completeness, that's the full version. I'm about to go on to doing the first law now, so I'm just going to take 5 minutes to give both me and everyone else a break. So I'm going to fill up my water, and let's come back in probably around 5:07 to continue. I mean, I've got the email. I'm giving the lecture. I've been thinking, and I'm pretty sure the to the question before, the time-like killing vector field in everything we've been doing since that first integral only needs to be time-like at infinity, and even for that first integral, it may only need to be time-like at infinity. And so, yeah, I knew I was wrong. It's a good question. Thanks for asking. Okay, so now we're going to derive the integral form. First law, which will be used in our derivation of the differential form. We're going to consider a curved black hole, which is the unique solution for an uncharged spherically symmetric spacetime. We're going to sketch the conformal diagram just because it's fun. And that continues up. This is our black hole region. This is our exterior universe. It's the white hole region. And it continues down. Of course, this is unphysical because black holes don't exist eternally. They form from collapsing matter. And so matter is going to start at time like infinity and collapse towards the singularity. And so we're going to replace most of our diagram with collapsing matter. So we can do a conformal transformation to bring r equals 0 vertical. And then it's going to hit the singularity. This is a Cauchy surface. This is all the matter. This is our model, where the final mass and angular momentum of the black hole are determined by the mass and angular momentum of the collapsed matter, of course. Now, I've drawn a Cauchy surface on here, which intersects the horizon after all the matter has crossed it. So we're now vacuuming the exterior solution, called this sigma. Let the event horizon be given by curly h, and let straight h be the intersection of the event horizon and our Cauchy surface. We know that Kerr admits a time-like killing vector field, which is time-like at infinity, psi A, and a space-like azimuthal killing vector field, psi A. That was proven in Hawking in, I think, 73, but feel free to correct me if I'm wrong. I'm not good at history. That there's another killing vector field which is tangent to the generators of the event horizon on the event horizon. And this killing vector field is chi equals xi a plus omega h psi a. Where omega h is interpreted as the angular velocity of the black hole. These killing vector fields are going to be used to calculate, as we saw in the Komar intervals, the mass and angular momentum of our Kerr black hole. I won't write down the, actually no, I will write down m equals, so we know that this is our expression. the mass of the asymptotically flat space-time, where S is a two-sphere infinity. We want an expression for M in terms of state variables, the area of the event horizon, and J, the angular momentum of the black hole. To get this, we apply Stokes' theorem in a particular way. Imagine S is a surface up there. Then it's bounding the entirety of our Cauchy surface. So we can use Stokes' theorem to write our mass as an integral over our Cauchy surface, sigma, d, cd, c, xi, d. Now we're going to split this into two parts. So our Cauchy surface, with a point H here, we're going to call this sigma int, which is the interior region, which is the bit inside the event horizon, and sigma ext, which is the region exterior to the event horizon. And so then we'll split the integral into a bit over sigma int and a bit over sigma ext. Then we use Stokes' theorem again, and we realize that we can now use the integral over H. This now bounds the interior region, sigma x, sigma int. And so we get M equals. Pardon?
It may be a naive question, but can we embed a Cauchy surface, full Cauchy surface inside the event horizon? Is that Cauchy slice, or I mean, in core black hole, can we embed some?
Yeah,
Cauchy
there's no problem with that. I mean, like look at the diagram. Every causal vector is going to intersect it.
But eventually it will hit the singularity at some point of time. So in reverse way, I think.
I'm not sure what the question is, but it's fine. This is a Cauchy surface for the relevant region.
Okay, it means it's also a globally hyperbolic inside. If we can embed some Cauchy surface.
I mean, things might get weird when we get particularly close to the singularity. I don't know, but yeah, for the region we're interested in, it's going to be fine. Actually, I don't think it gets weird. I think it's fine. I think it's globally hyperbolic inside as well.
Thanks.
So yeah, so we've split this integral into sigma ext. So this is our just integral over the exterior bit. Plus minus, the minus just come from, again, the correct orientation. Integral over H, sigma A, B, C, D, sigma C, D. Okay? Where H is now this part of the event horizon. And there's no exterior derivative, of course, because we've used Stokes' theorem again. Let's treat the first term. So this is going to be equal to just writing the exterior derivative, sorry, first term. Writing the exterior derivative explicitly. Which, using the same result as before.
Sorry, could you please repeat the splitting part of the sigma? So you have the exterior part, the horizon, but what happens to the interior sigma in?
What happened to sigma int? So we've applied Stokes' theorem again on sigma int, and we're now integrating over the event horizon, the intersection of the event horizon and the Cauchy surface, which I've called straight H, which by Stokes' theorem, so you have the exterior derivative has left that integral because we've applied Stokes' theorem again.
Right,
And so
but then the sigma int has two boundaries, right? Like one is one
because at the center of it is r equals 0. And so it's just the event horizon is just covering it all. It bounds the whole region.
Okay, and so the split was between sigma int and sigma exterior, and then the horizon also, right? At the horizon. And
Yeah.
there is an exterior derivative for the horizon term. What happens to that? So the sigma int you wrote as, by the Stokes theorem, you wrote as the integral over h. But then there was an integral over the horizon, the curly h. If I got it right.
There's never been an integral over curly h.
Okay.
Curly h is the entire event horizon.
I see. Okay.
Straight h is the intersection of the event horizon, and curly h, which is the entire event horizon.
Okay.
Glibly, I'll refer to straight h as the event horizon, but that's of course not. That's me speaking quickly because it's convenient.
That's one particular cut or slice of the event horizon.
Precisely.
Okay.
Sorry if I misspoke at some point, but it's convenient to call straight h the event horizon in most situations. Okay. By the same result as we derived before, we can write this as R. RAB xi, sorry, RED xi d e epsilon e a b c, which by Einstein's equation will be written as this. T ED minus a half T, where T is just the contraction of the set energy tensor. Okay, so this is our first term. Now let's deal with the second term. We're going to use our Killing vector field on the horizon, which the Killing vector field which is tangent to the generators of the event horizon. And so taking the second term, it's equal to 1 over 8 pi integral over h epsilon a b c d chi d minus omega h 1 over 8 pi integral over h epsilon a b c d c psi. Oh, that would be better. Psi d. Now you'll notice that this is just the Kolmogorov integral for j, and so we can write 1 over 8 pi a b c d c chi d minus omega h j h. Sorry, I forgot factor for 2 minus 2 omega h j h. Great, so we've got one of our state variable terms. To evaluate the first term in this, note that the volume element on H AB is going to be given by contraction of the volume element on the whole space-time and the two vectors, unit vectors, which are normal to it, which are going to be n, which is now I'm defining as the tangent. Write it down. N is tangent to the future directed null curves normal to H, and chi is our generators of the horizon to which it's normal because they're not. And we normalize this so that NA chi A equals -1. Therefore, epsilon AB contracted over epsilon AB CD, which is the volume form for the whole spacetime. Now plus C psi D. That I'm just writing what I just stated. C D. Now plus C psi D. Now we can contract using the contraction of volume forms I defined ages ago now, which I think was 1, using 1, minus 4C, NC, chi D, now plus C, chi D, which is minus 4 kappa by our definition of the surface gravity, which we met on Wednesday. And so we can write this integral over the derivative of the generators of the event horizon as we're just rewriting this, separating it into 2 bits. And this is minus kappa integral over the volume form for the horizon, which is of course just going to be the area of the event horizon. And so we can write the first law in integral form. M equals, let me start early on to make sure I fit it all in. M equals 2 integral over sigma x TED minus a half T delta ED psi D I'm sorry, ABC plus 1 over 4 pi kappa A plus 2 omega HJ H. Now this is a supernatural interpretation, with the first term being the contribution to the mass of the spacetime by the matter that's in the exterior region of the outside the event horizon, and these other 2 terms are the contribution of the black hole. So if I now stipulate that this is vacuum in the exterior region, I can write down the integral form in vacua, which is m equals 1 over 4 pi kappa A plus 2 omega H J H. Great, good job, Buzz. Let me just mute my email, sorry. But this expression holds little philosophical interest for us. I mean, we're doing a course on black hole thermodynamics. How is this relevant to black hole thermodynamics? It's not even formally analogous, right? Because the first law of thermodynamics is only well stated in differential form. There's no good notion of the absolute amount of work in the system or the absolute amount of heat flow. There's only changes, and I haven't talked about any changes yet. These are constant terms of a stationary Kerr black hole. In order to draw the analogy between black hole mechanics and black hole thermodynamics, we need the differential form, which we derive now. So, differential form. So what we're going to imagine is we've got 2 different spacetimes. MG.
Sorry, can I ask a question here before we proceed? So
Yeah.
I think the idea that the existence of sigma was crucial here, right? Like the existence of Cauchy hypersurface was crucial. So is this to say that for non globally hyperbolic spacetimes, we don't have the first rule?
This is a nice question about idealization and representation in general relativity. We always do things with globally hyperbolic spacetimes and stationary spacetimes and whatnot. And of course, things are much messier. For example, black holes evaporate, which in our current models ruins global hyperbolicity. Modeling how failures of global hyper, but I mean, black hole evaporation is only a prediction of quantum field theorem curved spacetimes.
Yes.
And in that situation, you can recover without global hyperbolicity. You can recover a framework of quantum field theory on curved spacetimes. You just have to define globally hyperbolic patches and make them link together. And the standard physicist's line is going to be, look, I'm always going to be able to model a curved black hole as in a globally hyperbolic region, right? Infinity doesn't actually mean infinity here. Like, we're not actually infinity. It's a finite distance where we can model it as flat. And so they're going to figure out ways to approximate it and de-idealize it. Whether you think that means it's crucial because it's part of the formal framework, or whether you think it's just to make the maths easy and it isn't really crucial, interesting questions. And they're worth thinking about. I don't have a more formal answer for you, I'm sorry.
Yeah, okay, thanks.
I mean, hopefully if I get time in lecture 6, I'll talk a bit about how I think these sorts of things affect derivations of Hawking radiation. But I mean, I've got lots of ideas for lecture 6, so we'll see. Okay, we're gonna have two spacetimes, mg and mg plus delta g, where delta g is some perturbation. We define a tensor HAB as the inverse perturbation metric. And the way you should imagine HAB is as a tensor field on this spacetime, the original one. Now we define the vector VA, different to our previous VA, of course. Previously it was the full velocity of a particle, now it's just totally different. Delta nabla B, HAB, GAB, H, where H is the contraction over the perturbation metric. Now, I state without proof that nabla A VA is 0. This is just the trace of the perturbed Einstein equation. And so this follows from the fact that it's true for that. So this is true by Einstein's equation. If you want to look at perturbed general relativity, go to Wald, 1984, chapter 7. But I state this without proof. We also have nabla A xi A equals 0 by Koenig's equation. For stationary perturbation, so for perturbation which doesn't change along time like Koenig vector fields, we have the Lie derivative of VA with respect to I shouldn't have the index in this. With respect to xi equals 0. Okay, but the Lie derivative of a vector field with respect to another vector field in a torsion-free spacetime is just the commutator. No, xy, where does that come from? And so a commutator of xi with v is equal to 0. With this, we can prove a lemma. So the exterior derivative of epsilon b, c, d, e, v, d, psi e, a equals 0. That's not a hard proof, and so I'm not going to do it. It just uses these three properties. So just moving down. Okay, so let's take, we're going to use Stokes theorem again. Sigma is going to be some three-dimensional volume bounded by two spheres, two spheres. So sigma equals sigma dot 1, sigma dot 2. Then obviously, by Stokes theorem, V dxi e is equals 0 by our lemma. It's also equal by Stokes theorem to V dxi e minus, I've run out of room. And go below. Of the integral of the two bounding two spheres, d v d psi e. So these two are equal to each other, of course. Now, let Cauchy surface be our Cauchy surface from before. Let sigma 1 dot be our Cauchy surface, be a two-sphere at infinity, which was S. And let sigma 2 dot be H, the intersection of the event horizon with the Cauchy surface. And so we get, writing this down explicitly, integral over S, our surface at infinity, psi e, and we're just going to write V out in full. V H, integral over H, epsilon, B, C, D, E, psi e, blah, blah, S, H. FD minus G, FD, H. So you've got our integral, same integrand, but our integral over the intersection of the Cauchy surface and the horizon, and our two surfaces at infinity. Now it's proven, I'm skipping this bit because it's not particularly nicely when Bardi and Carter and Hawking don't do any detail in the paper, it's just maths churning through. Proven in Bardeen, Carter, and Hawking, 1973.
Sorry, it's not obvious to me why the sigma 2 dot integral appears with the opposite sign.
Pardon?
So the splitting of sigma that you have done via Stokes theorem.
Mm-hmm.
So it's not obvious to me why sigma 2 dot appears with the opposite sign, the minus sign.
It doesn't make rotation work out. So if I've got this, if this is my region, then I'm sort of thinking about if you think about Stokes theorem intuitively, you're thinking about what's going out and what's going in. So you go, what's coming out of here minus what's coming in here, calculates the overall movement through the space-time. So you just make the orientations work. So it's proven in Bardi and Carter and Hawking, 1973. Now the left-hand side is equal to 8 pi dm, and the right-hand side is equal to minus 2a d kappa minus 16 pi jh d omega H. Okay, thus, just writing this in slightly different form. Minus 2A d kappa minus 16 by JH d omega H. Okay, now returning to our integral form in vacuum, I'll write it again. If I'm saying for integral form, m was equal to 1 over 4 pi a kappa plus 2j d omega. Just doing chain rule on this, we get dm equals 1 over 4 pi dA kappa plus a d kappa plus 2 dj h omega h plus jh d omega h. Okay, and now we're going to add this equation and this equation together. Okay, so obviously going to get 2dm on this side. Then if you look, our first term up here is minus 1 over 4 pi a d kappa. And we're going to have a 1 over 4 pi a d kappa term here. So they're going to cancel. And here we're going to have a minus 2 jd omega term here. And we've got a 2 jd omega term here. So they're going to cancel. And so we're going to have 2 dm equals 1 over 4 pi kappa dA plus 2 omega h d jh, and then just dividing by 2, dm equals 1 over 8 pi kappa dA plus omega h djh, which is our first law in differential form. Good. So what have we really done? We've modeled a perturbation on our space-time, which is changing the black hole very, very slightly. Just stretching out and seeing how adding a small perturbation to metric, what's sort of the consistency equation? How do things have to balance to make the space-time still occur? And then we've got this lovely differential equation, which, as we said at the start, is at least very formally analogous to the first law of thermodynamics. You can add a term for electric potential on charged black holes, and it can be generalized to non-stationary perturbations and non-vacuum spacetimes. That's obviously more work than I'm going to do here. But yeah, it's very nice. So I mean, anyone who wants to leave now, I wouldn't be offended if you've seen the first law of black hole mechanics. But I'm gonna, in sort of 15 minutes, just go through one other formulation, which is super fast and super clean and quite nice, and takes a totally different approach, but uses the no-hair theorem. And so if people are interested, I'm going to go through that now, but I'm aware I've been talking for about an hour and 40 minutes. If people are tired and want to leave, do feel free. So this is the partial derivative method. So this is going to rely on the so-called no-hair theorem. And the heuristic statement of the no-hair theorem is that a black hole is completely described by 3 parameters: its mass, its charge, and its angular momentum. However, and maybe I'm being a bit pedantic here as a philosopher, but the no-hair theorem is a misnomer. There are in fact many theorems which contribute to the impression that black holes are completely by these 3 parameters, but there's no one theorem which exactly proves what's stated in the heuristic version. therefore, like a better name is maybe the no-hair conjecture. I mean, this is emphasized by the fact that in recent times it's been called into doubt that it's true, and so you're not going to have a theorem for it. An example of a foundational theorem which contributes to the no-hair conjecture is the following. If Mg is a stationary, axisymmetric, asymptotically flat vacuum spacetime, suitably regular on and outside a connected event horizon, then Mg is a member of the two-parameter curve family of solutions, where the two parameters are M and J. And the limitations of what I just said are super clear. It only applies to vacuum spacetimes and asymptotically flat spacetimes and whatnot. And so it doesn't guarantee the conjecture holds for true astrophysical black holes. I mean, they're obviously not vacuum spacetimes. Nonetheless, the results have been generalized quite a lot, and although it's completely general proof, the conjecture isn't available, the support for it is extremely strong. And so it's worth it. And in this we're going to assume that the conjecture is true. So from the no-hair conjecture, which we're considering as a theorem here, we can write the area of a black hole is equal to a function of M and J. I'm again taking the charge to be 0, and I'm going to drop the Q equals 0 subscript throughout because it'll just be clunky. We're continuing with our uncharged assumption. So then, assuming that this function is differentiable in both variables, we can write by the chain rule dA is equal to partial dA by dm at constant j, dm plus partial dA by dj m dj. Now, we can't use our integral form of the first order to evaluate this because that's not just a function of two variables. And so instead we use results from the analysis of the Kerr metric. I've got the Kerr metric written down in my notes, but I mean, I want to be kind to myself, so I'm not going to write it down. Feel free to Google it if you want to see it. But there's an important term in it, which is delta equals r squared minus 2mr plus a squared, where a is equal to j over m. And there's a coordinate singularity in the Kerr metric at delta equals 0. When you solve this equation, you find r takes two values. R equals m plus minus root of m squared minus a squared. These correspond to an inner and an outer horizon of the Kerr metric. These both have super interesting properties, and there's loads of resources which can tell you about them. Again, the Ward book is the classic. There's a recent, I think, Matt Visser paper which does like a complete analysis of the properties of Kerr. I recommend it. But we're only concerned here with the outer horizon, which is R plus. And that's the radius at which null geodesics cannot escape, the standard definition of the event horizon. So we want to know the area of this event horizon H, defined by R plus. And so the induced metric on H, which is again the intersection of the event horizon and some Cauchy surface, such that dt equals 0 will be H equals G sigma sigma d theta squared, d G theta theta plus G phi phi plus d phi squared. Well, these are the terms taken from the Kerr metric. Okay. The volume form on this two surfaces is then obviously going to be epsilon theta phi, and then the square root of the norm of the induced metric. using this, we can calculate the, just muting the chat, calculate the area of H. Say A equals the integral over R and R plus. Let's go g theta, g phi, d theta, d phi, which is equal, if you run it through, oh, I'm moving my notes, not the screen, to 4 pi r plus squared plus a squared equals 4 pi m squared plus 2m m squared minus a squared m squared minus a squared plus a squared, writing it in full, is equal to 8 pi m squared plus m squared minus a squared. So this is from the analysis of the Kerr metric, and it's what we're going to be using to, it's only a function of m and j, so we can now use this to compute our partial derivatives. I state without proof that the surface gravity at the event horizon in the Kerr metric is given by this equation, and similarly the angular momentum is given by this, angular momentum at the event horizon. And computing our partial derivatives, we find dA by dm at fixed j equal to 8 pi over kappa, and dA by dj over m at constant m, sorry, it's minus 8 pi omega h over kappa. So now we have, summing this all back in, dA equals 8 pi over kappa dm minus 8 pi omega h over kappa dj, which obviously gives us back exactly what we want. So from the no-hair theorem, if we just take it as true, then we get the first law back out again, which is a super nice proof. I mean, that's all I've got today. Are there any questions?
Yeah, yes. I mean, you're saying, I mean, this form of first law looks to be true where entropy is proportional to area, right? But we know that entropy is not always proportional to area. I mean, in all theory of gravitations, in GR it values that entropy is proportional to area. Shouldn't we have a generalized entropy or something like that?
I'm really sorry. Could you say that again? I didn't catch it.
I'm asking like this form of first law should be true where entropy is proportional to area, or it's valid everywhere. I mean, in general, shouldn't we get instead of dA, we should get some generalized entropy ds?
You're asking. I keep hearing you saying generalized entropy. You're asking about the generalized second law.
Yes, yes.
Yeah. So when we
this
inevitably draw an analogy between the laws of black hole mechanics and the laws of thermodynamics and develop the laws of black hole thermodynamics, there's going to be a ds in this term. We're going to get a ds. That is going to be the entropy of the black hole, right? And you're right. People will often write down something really that S generalized is equal to S black hole plus S norm, the normal S entropy of the universe. And they say this is the thing that obeys the second law of thermodynamics proper.
No,
but when we draw the analogy, the ds is going to be this. It's going to be the entropy of the black hole. I'll stop sharing. Any other questions? Curious how many people have survived. Only 6. Awesome. Okay, if that's it. Oh, a question.
Sorry. Maybe you'll cover this in the next session. It's just that if we let the Hawking radiation happen and the area of the black hole diminishes, does that mean that the entropy still increase because of the other S you wrote in just the equation you wrote before?
Yeah, exactly. So
Okay.
the generalized second law is what seems to hold because of Hawking radiation. Exactly. Yeah.
Okay. No,
Because
that was the question.
because black holes are incredibly entropic, highly entropic with their mass. So when you throw a cup of tea into a black hole, the entropy of the universe increases a lot. And then Hawking radiation is even more entropic. And so when it radiates that mass away again, it gets even more entropy.
Okay. Thank you.
You're welcome. Okay, I'm exhausted, so we're going to end there. Thanks very much, everyone, and I'll see you a week next Friday. Have a good week.
Thank you for the talk.
Thank you.